Now we are going to study the dielectric materials. Capacitors have a non-conducting materials called the dielectric between conducting plate. Due to charges on conducting plate, induce the positive and negative charges in the dielectric material arise near conducting plate. So capacitor has a positive charge in the upper plate and a negative charge in the lower plate. Because of this positive charge, negative charge is induced in the upper side of the dielectric. On the other hand, positive charge are induced in the lower side of the dielectric. This reduces the electric field between the plate. So between the positive charge and negative charge, we have electric field from the up to the down. Inside of the dielectric, positive charge and negative charge is induced. Electric field with the opposite direction is induced. So total amount of the electric field is the sum of these two electric fields. Dielectric constant. So if we don't put any dielectric, originally electric field is sub 0. If you substitute the dielectric inside of the two conducting plate, as I explained, charge are induced. So this is positive charge, negative charge are induced. The electric field is cancelled out here. So sum of the electric field is cancelled out. Magnitude of the electric field is decreasing by the effect of the dielectric. Charges on conducting plate remains constant during the introduction of the dielectric. So Q is constant. But the electric field decreases due to the induced charges in dielectric. The ratio of E sub 0 over E has to be the larger than 1. We call that this is dielectric constant, K. So if you multiply the D in the up and down, so this is equal to B sub 0 over V. So dielectric constant is equal to the ratio of the potential difference. Also from the B sub 0 over V, B sub 0 is a Q over C sub 0. B equal Q over C. And Q is going to be cancelled out. It's going to be C over C sub 0. This is dielectric constant. Dielectric constant is a ratio of the electric field, ratio of the voltage difference, ratio of the capacitances. So dielectric can maintain two conducting plates at very small separations. So Coulomb attractive force acting between the two plates. So we need some materials to keep the two conducting plates away from each other. Dielectric works well to separate the two conducting plates. The second point is dielectric can sustain high pressure difference. So ratio of the potential drop is given by the dielectric constant. And the capacitance becomes larger because dielectric constant is a C over C sub 0 is larger than 1. For example, this is the value for some materials for air compared with the vacuums, nearly equal to the vacuum, 1.00059. In the case of the glass, 5 to 10. In the papers, between 2 and 2.6. The permittivity. Charge density, sigma equal Q over S. S is the area of the plate, doesn't change. The induced charge is a negative sigma sub I in the upper side of the dielectric. And the lower side of the dielectric, this becomes positive sigma sub I. So negative sigma sub I. So net charge density, if you sum up these two, it becomes a sigma minus sigma sub I on the upper side. The electric field without a dielectric is expressed sigma over epsilon 0. And by the introducing the dielectric, electric field is changing sigma minus sigma I over epsilon 0. So from these two equations, you can write down the dielectric constant. K equals E sub 0 over E. Then substitute here and here. It becomes sigma over sigma minus sigma sub I. From these equations, E equals sigma minus sigma sub I over sigma E sub 0. And E sub 0, this is equal to the sigma over epsilon 0. So it becomes sigma is going to be cancelled out. Sigma minus sigma sub I over epsilon 0. Also, you can express the E equal K over E sub 0. Also, you can use this expression equal sigma over K epsilon 0. Then, by introducing permittivities, epsilon equal K epsilon sub 0, this expression is sigma over epsilon. Electric field is expressed in the materials the sigma over epsilon. And the epsilon equal K, the electric constant times epsilon sub 0. Then how can we modify the Gauss law in dielectrics? So in the case of the electric field is a sigma minus sigma sub I over epsilon naught. This is equal to the sigma over K epsilon sub 0. By using the permittivities, we can express the sigma over epsilon. So instead of the epsilon sub 0, if you use epsilons, we have exactly same expressions for the Gauss law in dielectric. Okay, just replacing the epsilon sub 0 to the epsilons, we can write the Gauss law in dielectrics. Okay, this is the end of this session.